So in our next video, we're going to focus just on normal curves, start learning more characteristics and properties of these normal curves, which again will be the focus for the rest of the chapter as well. So as we saw in the first video, a normal curve is just a symmetric single-peaked bell curve. And so again, it's symmetric, it's got a single peak, and it's bell curved. And so it's literally, something along those lines. And like we talked about, right in the middle of that, the reason it's called a normal curve is because the data is normalized. And so the mean and the median of that data is right in the middle of that normal curve. Okay, and so, but this data, the data that can be used has to follow this curve. Okay, so if there is a data that is more of a skewed distribution, like we saw something like that, or the other direction, no, that's not a very good example there. Let's try that again. There we go. Then these properties that we're going to go over today for skewed distributions don't apply, but they only apply to normal distributions, or like what we saw again in the last video, a uniform distribution where every grouping, every histogram bar or every bar graph is the exact same height. Okay, so again, that's what everything that we're going to go over from here on out only applies to normal curves and uniform distributions. So a couple of places where this shows up a lot is your SAT, ACT, MCA scores. Any sort of standardized testing typically follows a normal distribution, as well as biological populations. And the examples just go on and on of where this can be applied, which is ultimately why it is one of my favorite things to talk about. It's a good approximate for chance outcomes like tossing a coin or rolling a die. If you toss a coin once or twice, let's just say, it's not guaranteed. In fact, you only have a 25% chance that you are going to get a heads and a tails. And so it's not even likely that will happen. But the idea is that if you toss a coin 1,000 times, that it becomes more uniform, meaning that the breakdown is closer to 500 and 500. If you toss it 10,000 times, it'd be closer to 5,000 and 5,000. And same thing with rolling a die. And then many statistical inferences are based on normal distributions. So again, population approximations are based on normal distributions. Okay, any data that is shaped like a bell curve can be interpreted using a normal curve, which again has many different characteristics that we're going to learn about today. So again, the mean median happens at the single peak. It's right in the middle. It's a unique case where the mean equals the median. Okay, typically in a normal distribution there are no outliers, or there are extremely few outliers. Okay, so typically that's what happens with normal curves. The point of a normal curve is to visualize standard deviation. So in one of our one of our last videos in chapter 3, I believe, I think it was the last video, we talked about standard deviation and what that meant. The normal curve visualizes standard deviation. And so the standard deviation of a data set can be seen where there's a change in curvature on either side of the mean. So there's a couple examples here, and it's hard to be exact, but the point of a normal curve is to make estimations and approximations about data. It is not to say exact stats or to come up with exact answers, but it's a way to summarize and approximate data. Okay, and so again, on an estimate here is that it's where the curve starts to change, get a little bit steeper, and so right about here would be one standard deviation from the mean. Okay, and then again, if I had to estimate, I would say right about here is another standard deviation, right where it starts to kind of flatten out there. But if it's more steep of a data set, okay, you have there, and then again, if I were to try and estimate, it would be right around there, maybe actually a little bit further over, like there is where the third, another deviation happens, okay? And so again, what a normal curve does is it allows you to estimate or approximate, it's not exact, but estimate or approximate and visualize standard deviation. So we have this rule, 68, 95, 99.7 rule. What this rule states is that 68% of the observations will fall within one standard deviation. And I want to emphasize approximately 68% of the observations fall within one standard deviation. Okay, so if you look at your normal curve here, all right, this is visualized here. 68% of your data. So let's just use an easy number. If we had, I'm going to say 1,000 people. If we had 1,000 people take a test, 680 people would fall between one standard deviation from the mean, whether that's above or below. 680 people would fall in this lighter blue chunk, in this lightest blue chunk. Okay. Then approximately 95% fall within two standard deviations. So, and that encompasses the first group, but 95% of people of the group will be in between two standard deviations from the mean. Okay? And so again, that would be 950 people in our example of 1,000 people. And then 99.7 means 997 people will fall within three standard deviations. Okay? And again, this is the purpose of the normal curve, is to visualize how data is grouped together and approximate. Okay? This took years and years and years of studying and research to come up with this 68, 95, and 99.7 rule. It took countless numbers of studies to do this. So this isn't just based off of one random thing. This is based off of various normal curves throughout time that follow this pattern. And if we think about it here, let's just think in terms of test scores, since that's kind of where our mind is, especially right now around testing time. Okay? So you have the average test score, ACT. In fact, is it going to let me? Yes, all right. Average ACT score. All right, let's see. I just want okay, December 8th, 2019, blog.prepscholar.com. That sounds a really good site to use. It says the average ACT score is 20.8. Okay, so again, right in the middle is the average. And so if we use the ACT scores, the average ACT score was 20.8. And again, that's right in the middle. So what this implies is that, again, if I just use 1,000 people, 680 people will be within one standard deviation of this score. Now, I didn't Google the standard deviation, so we don't know what that is, but 680 people would be within that range. 950 people would be within two standard deviations, and 997 people, so everyone but three, would be within three standard deviations. And think about that. If we're thinking ACT scores, if you score three standard deviations above the mean, that's probably going to be pretty close to a 36. And so there's not many people that are going to be higher than that, right? And vice versa. People get different scores, but not very many people do so bad on the ACT that they're scoring, in the low single digits, right? That just doesn't happen. And so 997 people will fall within this data set. The extra 0.3% fall on the outside of the data set because, again, that just doesn't happen very often. Okay? So in this example, it says approximately how much of the data falls to the left of the one standard deviation from the mean. So here's where we need to understand how this chart divides up data. Okay? Remember that this line here at 0 divides the data right in half. Okay? And so if this whole range is 68%, then this part of that range, just from, let's try to draw that a little bit straighter, but from the black line to the green line, that part of the range represents half of 68, so 34% of the data falls above 1 standard deviation. Okay? And so this question asks us approximately how much of the data falls to the left of the point 1 standard deviation from the mean. Okay, so here's our 1 standard deviation. It's asking how much falls to the left. Okay, well again, in this chunk, that's 34%. And then in this chunk, that's 50%. So if I add those two together, in every normalized data set, it doesn't matter what it's representing, if it's the shape of a symmetric single-peaked bell curve, 84% of the data will fall 1 standard deviation or below the, or less than 1 standard deviation above the mean. Okay? Every data set. And again, that's the point of the normal curve, and that's the point of these patterns, is that if your data fits this single bell curve shape, and it's symmetric, then we can make these types of generalizations about every data set that follows that pattern. Okay? I know we don't use the book anymore, but just in case you do see it for future reference, your mean, which you saw last chapter as well, is represented by kind of a U that has this like extra thing. Your standard deviation is represented by sigma, which is like a kind of like something that looks like that. Okay. Just so you know for future, I don't recall if you'll actually see that now that we don't use the book, but you know, especially if you are working in a higher level math class at some point, you will definitely see those two symbols used for mean and standard deviation. Okay, and so your formula would actually look, if I put it in terms of math symbols, will actually look just as simple as that. Okay, that was just kind of an FYI when we were in the book. I don't know if we'll actually see it, but like I said, it's not bad information to know. Okay, so let's look more at applying this information. All right, let's look at an example together. It says about 1.4 million juniors took the PSAT. The mean was 46.7, and the standard deviation was 11.3. It says, what range of scores should we expect 68% of the test takers to fall within? Okay. Well, again, 68%, using that rule, the 68, 95, 99.7 rule, 68% will fall within 1 standard deviation. Okay, and I'll just of the mean to clarify that. And so if the mean is 46.7, then that means 68% of scores will fall between, let's see, that is 58. And on the other end, let's see, let's pull out the calculadora quick. 46.7 minus 11.3, 35.4. And so 68% of test takers will fall in between 35.4 and 58. And so what this would look like on our bell curve, okay? There's the middle of our bell curve, and it said that the mean was 46.7. And so if I go 1 standard deviation above that, so that's 1 standard deviation above, that's a score of 58. And if I go 1 standard deviation below, which we would say is -1 standard deviations, that is 35.4. And so using our approximation, we are estimating that 68% of test takers will fall between those two scores, 35.4 and 58. Okay, so I took the mean. I noticed that 68% is typically one standard deviation from the mean. So then I took that one standard deviation, which was 11.3, and added it and subtracted it to the mean, and that's how I got my range. And so my formal answer to this question would be between 35.4 and 58. What percent of scores are less than 58? So now we're kind of going the other way. We are given in this case, we were given the percentage. In this case, we're looking for a percentage. And so again, you need to understand that when you look at 58 in this scenario, that is one standard deviation above the mean. Okay, and so here we are, there's 58. And if I'm looking for percent of scores that are less than that, I'm looking for what percent are this way. Okay? And that ends up being kind of the same problem that we just looked at. Remember, if this is the mean right here, 34% fall in this chunk, 50% fall below the mean. So then that would, once again, we would estimate that 84% would score below a 58 on the PSAT. Okay. 84%. What percent of students would score less than 13? Okay. Well, if we consider what 13 represents, okay, 13 is about 3 standard deviations below the mean. Okay. Now, if you're wondering the long way how we can figure that out, basically what I did was 46.7 minus 11.3, and that gave me 35.4. If I subtract it again, let's make sure I get this right, I get 24.1. Oops. If I subtract 11.3 again, I get 24.1. If I subtract 11.3 a third time, I get 12.8, which isn't exactly 13, but that's why I said it's about 13 standard deviations below the mean. Okay? And so again, if we think about our chart, I'm going to come over here to do that. Right now, we are way over here for a 13, and we are looking at what percent fell below that. Okay? Well, remember that in between -3 standard deviations and +3 standard deviations is 99.7% of the data. So that means that that 0.3% are on each side, and that if it's 0.3 total divided by 2, that not 15%, but 0.15% of the data was below that standard deviation. Okay, so again, think about it. There's 99.7 in between the two bars. So on the outside of the two bars, to the right and to the left, there's a total of 0.3%. But what the normal chart does is divides that in half. So 0.15 on this side and 0.15 above. And again, think about that. We are talking about a very small portion of students that would do very bad on the PSAT, or a very small portion of students that would do very well on the PSAT. Okay, so it makes sense that those numbers are so small. So in this 4.4 and 4.5, the biggest thing that you should come away with is an understanding of our 68, it's supposed to be an 8, 68, 95, 99.7 rule, and how to use that, how to interpret that. And again, the examples that we did on the last page go in both directions. The first example told you it was 68% and you had to find the range of scores. And then the last two examples gave you a certain score and said what percent of students would fall in that range. Okay, so make sure before you move on that you have a really good idea on when you look at this normal curve, that you have a really good idea on how it's broken down. In other words, whoops, make sure that you really understand what we talked about here and how that works. Okay?